well this neural network works with the current setting of parameters. Now I would like to make it even more respectable. So in particular, see these lines here, where we take the logits and we calculate the loss. We're not actually reinventing the wheel here. This is just classification, and many people use classification, and that's why there is a functional.crossentropy function in PyTorch to calculate this much more efficiently. So we could just simply call f.crossentropy, and we can pass in the logits, and we can pass in the array of targets y, and this calculates the exact same loss. So in fact, we can simply put this here and erase these three lines, and we're going to get the exact same result. Now, there are actually many good reasons to prefer f.crossentropy over rolling your own implementation like this. I did this for educational reasons, but you'd never use this in practice. Why is that? Number one, when you use f.crossentropy, PyTorch will not actually create all these intermediate tensors because these are all new tensors in memory, and all this is fairly inefficient to run like this. Instead, PyTorch will cluster up all these operations and very often have fused kernels that very efficiently evaluate these expressions that are sort of like clustered mathematical operations. Number two, the backward pass can be made much more efficient. And not just because it's a fused kernel, but also analytically and mathematically, it's often a very much simpler backward pass to implement. We actually saw this with micrograd. You see here when we implemented 10H, the forward pass of this operation to calculate the 10H was actually a fairly complicated mathematical expression. But because it's a clustered mathematical expression, when we did the backward pass, we didn't individually backward through the exp and the 2 times and the -1 and division, etc. We just said it's 1 minus t squared. And that's a much simpler mathematical expression. And we were able to do this because we're able to reuse calculations and because we are able to mathematically and analytically derive the derivative. And often that expression simplifies mathematically, and so there's much less to implement. So not only can it be made more efficient because it runs in a fused kernel, but also because the expressions can take a much simpler form mathematically. So that's number one. Number two, under the hood, f.crossentropy can also be significantly more numerically well behaved. Let me show you an example of how this works. Suppose we have a logits of -2, 3, -3, 0, and 5. And then we are taking the exponent of it and normalizing it to sum to 1. So when logits take on these values, everything is well and good, and we get a nice probability distribution. Now consider what happens when some of these logits take on more extreme values. And that can happen during optimization of a neural network. Suppose that some of these numbers grow very negative, like say -100. Then actually everything will come out fine. We still get the probabilities that are well behaved and they sum to 1 and everything is great. But because of the way the exp works, if you have very positive logits, let's say +100 in here, you actually start to run into trouble and we get not a number here. And the reason for that is that these counts have an inf here. So if you pass in a very negative number to exp, you just get a very negative, not negative, but very small number, very near 0, and that's fine. But if you pass in a very positive number, suddenly we run out of range in our floating point number that represents these counts. So basically we're taking e and we're raising it to the power of 100, and that gives us inf because we run out of dynamic range on this floating point number that is count. And so we cannot pass very large logits through this expression. Now let me reset these numbers to something reasonable. The way PyTorch solved this is that, you see how we have a well-behaved result here? It turns out that because of the normalization here, you can actually offset logits by any arbitrary constant value that you want. So if I add 1 here, you actually get the exact same result. Or if I add 2, or if I subtract 3. Any offset will produce the exact same probabilities. So because negative numbers are okay, but positive numbers can actually overflow this exp, what PyTorch does is it internally calculates the maximum value that occurs in the logits, and it subtracts it. So in this case, it would subtract 5. And so therefore the greatest number in logits will become 0, and all the other numbers will become some negative numbers. And then the result of this is always well behaved. So even if we have 100 here previously, not good, but because PyTorch will subtract 100, this will work. And so there's many good reasons to call cross entropy. Number 1, the forward pass can be much more efficient, the backward pass can be much more efficient, and also things can be much more numerically well behaved. Okay, so let's now set up the training of this neural net. We have the forward pass. We don't need these. Instead, we have that loss is equal to the cross entropy. That's the forward pass. Then we need the backward pass. First, we want to set the gradients to be 0. So for p parameters, we want to make sure that p grad is none, which is the same as setting it to 0 in PyTorch. And then loss.backward to populate those gradients. Once we have the gradients, we can do the parameter update. So for p parameter, we want to take all the data and we want to nudge it learning rate times p dot grad. And then we want to repeat this a few times. And let's print the loss here as well. Now this won't suffice and it will create an error because we also have to go for p in parameters, and we have to make sure that p dot requires grad is set to true in Python. PyTorch. And this should just work. Okay, so we started off with loss of 17 and we're decreasing it. Let's run longer. And you see how the loss decreases a lot here. So if we just run for 1,000 times, we get a very, very low loss. And that means that we're making very good predictions. Now, the reason that this is so straightforward right now is because we're only overfitting 32 examples. So we only have 32 examples of the first 5 words, and therefore it's very easy to make this neural net fit only these 32 examples because we have 3,400 parameters and only 32 examples. So we're doing what's called overfitting a single batch of the data and getting a very low loss and good predictions. But that's just because we have so many parameters for so few examples. So it's easy to make this be very low. Now we're not able to achieve exactly 0. And the reason for that is we can, for example, look at logits, which are being predicted. And we can look at the max along the first dimension. And in PyTorch, max reports both the actual values that take on the maximum number, but also the indices of these. And you'll see that the indices are very close to the labels, but in some cases they differ. For example, in this very first example, the predicted index is 19, but the label is 5. And we're not able to make loss be 0, and fundamentally that's because here, the very first or the 0th index is the example where ... is supposed to predict E, but you see how ... is also supposed to predict an O, and ... is also supposed to predict an I, and then S as well. And so basically, E, O, A, or S are all possible outcomes in a training set for the exact same input. So we're not able to completely overfit and make the loss be exactly 0, but we're getting very close in the cases where there's a unique input for a unique output. In those cases, we do what's called overfit, and we basically get the exact same and the exact correct result. So now all we have to do is we just need to make sure that we read in the full dataset and optimize the neural net. Okay, so let's swing back up where we created the dataset, and we see that here we only use the first 5 words. So let me now erase this, and let me erase the print statements, otherwise we'd be printing way too much. And so when we process the full dataset of all the words, scroll back down, the dataset is much larger, reinitialize the weights, the same number of parameters, they all require gradients, and then let's push this print.loss.item to be here, and let's just see how the optimization goes if we run this. Okay, so we started with a fairly high loss, and then as we're optimizing, the loss is coming down. But you'll notice that it takes quite a bit of time for every single iteration. So let's actually address that, because we're doing way too much work forwarding and backwarding 228,000 examples. In practice, what people usually do is they perform forward and backward pass and update on many batches of the data. So what we will want to do is we want to randomly select some portion of the dataset, and that's a mini batch, and then only forward, backward, and update on that little mini batch. And then we iterate on those mini batches. So in PyTorch, we can, for example, use torch.randint. We can generate numbers between 0 and 5 and make 32 of them. I believe the size has to be a tuple in PyTorch. So we can have a tuple, 32 of numbers between 0 and 5. But actually we want x.shape of 0 here. And so this creates integers that index into our dataset, and there's 32 of them. So if our mini batch size is 32, then we can come here and we can first do mini batch construct. So in the integers that we want to optimize in this single iteration are in ix, and then we want to index into x with ix to only grab those rows. So we're only getting 32 rows of x, and therefore
So rather than training on all of the 2,800,000 of the data, what it is doing is it is doing it in batches. It's not it's not supposed to be all so give me 32 elements between 0 to 9 to that.
therefore embeddings will again be 32 by 3 by 2, not 200,000 by 3 by 2. And then this ix has to be used not just to index into x, but also to index into y. And now this should be mini batches, and this should be much, much faster. So, okay, so it's instant almost. So this way we can run many, many examples nearly instantly and decrease the loss much, much faster. Now, because we're only dealing with mini batches, the quality of our gradient is lower. So the direction is not as reliable. It's not the actual gradient direction. Loss much, much faster. Now, because we're only dealing with mini batches, the quality of our gradient is lower. So the direction is not as reliable. It's not the actual gradient direction. But the gradient direction is good enough, even when it's estimating on only 32 examples, that it is useful. And so it's much better to have an approximate gradient and just make more steps than it is to evaluate the exact gradient and take fewer steps. So that's why in practice, this works quite well.
If you give us a might not be perfect. And will not be fully done. But still that direction is good enough for us to calculate some.
So let's now continue the optimization. Let me take out this lost item from here and place it over here at the end. Okay, so we're hovering around 2.5 or so. However, this is only the loss for that mini batch. So let's actually evaluate the loss here for all of x and for all of y, just so we have. Have a full sense of exactly how well the model is doing right now. So right now we're at about 2.7 on the entire training set. So let's run the optimization for a while. Okay, we're at 2.6. 2.57. 2.53. Okay, so one issue, of course, is we don't know if we're stepping too slow or too fast. So this 0.1, I just guessed it. So one question is, how do you determine this learning rate? And how do we gain confidence that we're stepping in the right sort of speed? So I'll show you one way to determine a reasonable learning rate. It works as follows. Let's reset our parameters to the initial settings. And now let's print in every step, but let's only do 10 steps or so, or maybe 100 steps. We want to find like a very reasonable set.
So if we see loss equation down like this and if we see that loss is not reducing but going up and then going down, it's the point one is huge. So if we can remember it, just 7 variables. So this is so and here, right, this is the value that we have for the rate. We are getting the gradient and we are changing the values here. Next iteration, right? We are changing and the rate is the rate is here. Next iteration, rate is that's what we are changing. This how much of a change, right? It depends on 0.1. If we give a very smaller value, it's slowly, our value will come down to the minimum loss. But if in case we are given a very high value, let's say 0 or 0.9, so what happens? If you change it, it might switch to the new value. This new value. I'm getting it. Might change the data to so high that so and it can't be very low as 0.001, then it will vary slowly, we'll see the value. So we need somewhere we need somewhat sane value so that we keep approaching towards the loss and everything. So that's where the question comes on, what is that best? Usually this is called as a learning rate. What should be the best learning rate that can help you reach this location?
Search range, if you will. So for example, if this is like very low, then we see that the loss is barely decreasing. So that's not
so that's one instance that I know that it is reducing very slowly because the value of learning rate is
that's like too low basically. So let's try this one. Okay, so we're decreasing the loss, but like not very quickly. So that's a pretty good low range. Now let's reset it again. And now let's try to find the place at which the loss kind of explodes. So maybe at -1. Okay, we see that we're minimizing the loss, but you see how it's kind of unstable. It goes up and down quite a bit.
So that's what up and down means. It is at times here, then here, then here, then here. We want it to reduce and bit substantially rather than very small.
So -1 is probably like a fast learning rate. Let's try -10. Okay, so this isn't optimizing. This is not working very well. So -10 is way too big. -1 was already kind of big. So therefore, -1 was like somewhat reasonable if I reset. So I'm thinking that the right learning rate is somewhere between -0.001 and -1. So the way we can do this here is we can use torch.length space. And we want to basically do something like this, between 0 and 1, but number of steps is one more parameter that's required. Let's do 1,000 steps. This creates 1,000 numbers between 0.001 and 1. But it doesn't really make sense to step between these linearly. So instead, let me create learning rate exponent. And instead of 0.001, this will be a -3, and this will be a 0. And then the actual LRs that we want to search over are going to be 10 to the power of LRE. So now what we're doing is we're stepping linearly between the exponents of these learning rates. This is 0.001, and this is 1, because 10 to the power of 0 is 1. And therefore we are spaced exponentially in this interval. So these are the candidate learning rates that we want to sort of like search over roughly. So now what we're going to do is here we are going to run the optimization for 1000 steps. And instead of using a fixed number, we are going to use learning rate indexing into here, LRs of I, and make this I. So basically, let me reset this to be, again, starting from random, creating these learning rates between negative between 0.001 and 1, but exponentially stepped. And here what we're doing is we're iterating 1000 times. We're going to use the learning rate that's in the beginning very, very low. In the beginning is going to be 0.001, but by the end it's going to be 1. And then we're going to step with that learning rate. And now what we want to do is we want to keep track of the learning rates that we used, and we want to look at the losses that resulted. And so here, let me track stats. So LRI.append LR, and loss side.append loss that item. Okay, so again, reset everything and then run. And so basically we started with a very low learning rate and we went all the way up to a learning rate of -1. And now what we can do is we can PLT that plot and we can plot the two. So we can plot the learning rates on the x-axis and the losses we saw on the y-axis. And often you're going to find that your plot looks something like this, where in the beginning you had very low learning rates. So basically barely anything happened. Then we got to like a nice spot here. And then as we increased the learning rate enough, we basically started to be kind of unstable here. So a good learning rate turns out to be somewhere around here. And because we have LRI here, we actually may want to do not not the learning rate, but the exponent. So that would be the LRE at I is maybe what we want to log. So let me reset this and redo that calculation. But now on the x-axis, we have the exponent of the learning rate. And so we can see that the exponent of the learning rate that is good to use, it would be sort of like roughly in the valley here, because here the learning rates are just way too low. And here we expect relatively good learning rates somewhere here. And then here things are starting to explode. So somewhere around -1 as the exponent of the learning rate is a pretty good setting. And 10 to the -1 is 0.1. So 0.1 was actually a fairly good learning rate around here. And that's what
Nice. Learning. So 0.0201, that is 10 to the power minus 3, and last it's 1, 10 to the power 0. Okay, it takes like this. So in range. Learning rate, and that's what I get. And
Is it perceptron low? Do you do that LRE?
okay, so it's exponents.
Exponent of the learning.
Sorry. Oh my god. Oh, sorry. So when it is 0.001, right? And here is the loss. Let's see, and this is where it kind of explodes. So yeah, somewhere in that 10 to the power minus 1, 0.1 is a good enough learning rate. The loss changes a lot. Into the 3 something to the power minus half is 3.1, 0.3 or something like that. So
Learning rate. And so we can see that the exponent of the learning rate that is good to use, it would be sort of like roughly in the valley here, because here the learning rates are just way too low. And then here we expect relatively good learning rates somewhere here. And then here things are starting to explode. So somewhere around -1 as the exponent of the learning rate is a pretty good setting. and 10 to the negative 1 is 0.1. So 0.1 was actually a fairly good learning rate around here. And that's what we had in the initial setting, but that's roughly how you would determine it. And so here now we can take out the tracking of these, and we can just simply set LR to be 10 to the negative 1, or basically otherwise 0.1, as it was.
It's 0.3. 2.35, something like
Was before. And now we have some confidence that this is actually a fairly good learning rate. And so now what we can do is we can crank up the iterations, we can reset our optimization, and we can run for a pretty long time using this learning rate.
Let's close it here. I need to go out, but that's what it is. So we are getting this error, this much of loss. I think what this gives us a sense of confidence here. If you see the loss starts increasing a lot more rather than coming down, so that is pretty huge value. Here it's somewhat fine. Okay, I think it will take some time to run. I will let you know what the loss I get here. Okay, thanks everyone.